Hello everyone, welcome back. So, it's a group problem, but if you're watching this video, it might be online, so go grab your dog, grab a pet, or a rubber ducky, and do the problem together. Or if you have friends or family members who are good at statics, call them up, but don't let them help you too much. Now, let's look at this and see what they've given us to solve this problem. So first off, I see the beam is supported by the roller at A. Okay, roller, smooth roller. And we got a pin at B. Okay. Roller only has a reaction force that is perpendicular to the surface that it's touching. So it would be directed like this. We got some angles, we could probably figure that out. And the pin support has a reaction force in the X and the Y direction. Other things that are weird, we've got a distributed load. Don't let it freak you out though, because it's a rectangular distributed load. The resultant of that distributed load will be pressing at the center of that, at the centroid of the shape. So just 2 meters from B. So we want to find the reactions. Now let's think about it. Okay, we're going to have two reaction forces here, one reaction force there, 3 equations, 3 unknowns we can solve. So let's get to it. Now it says to establish the XY axis system, and then draw a complete free body diagram of the beam. Apply the equation of equilibrium to solve for the unknowns. Okay, so here you go. You've got the answer now. Get to it. So I want you to take some time, try this out, and when you are done, come back and see how you did. So 3, 2, 1, and you're back. Hopefully. And let's see how you did. First off, we have to have that free body diagram. Now remember our distributed load. We found the resultant, which was 3 kilonewtons per meter, 4 meters. 3 times 4 is 12. And that goes at the centroid of my shape. It's rectangular, so that's right at the center. So 2 meters from B. Okay, now here we go. The issue you might have most problem with is trying to figure out, well, what is this perpendicular distance going to be? Well, look at this. It's 30 degrees from the negative x-axis. So kind of inverting that would be 30 degrees from the positive y-axis. Now it's not a perfect analogy. See, it's kind of like you're inverting it, but doing my best here. And with that, you will get this. Otherwise, if you really are struggling, I would say just try to do some drawings. Because you know this is 30 degrees right here, and you know that this is a perpendicular line. Okay. So this must be 60 degrees, which means that this line right here, which is also perpendicular, 90 degrees to that, has to be 30 degrees from that. So you can do the math, just draw some triangles and it'll help you out. Okay, now we've got to decide how are we going to solve this problem. What are we going to do? Which one's going to be the easiest one to solve? And sadly for this one, there's a couple of different ways you could do this. But none of them are absolutely perfect. The one that is probably the simplest is once again to start with your sum of the moments. Because in the x direction we have multiple forces, and in the y direction we have multiple forces. However, if we take the moment around point B, only our reaction force right here at A will have any components. However, you got to be careful. Because when you take this moment around point B, you have to realize that there is a horizontal distance, yes, but there is also a vertical distance, and that's not given. So you're going to have to figure out what that vertical distance is. Now they do that right here, but let's talk about it and figure out where they got all these numbers. So first off, let's talk about the horizontal distance we see right here. 4 meters makes sense. Why did they say 3 cosine of 30? Well, if I'm drawing a triangle right here, and this is my position vector, then this component on the bottom would be adjacent over hypotenuse, which is cosine of 30. So that's where this comes from. It's 3 meters long, so 3 cosine of 30. Similarly, over here we need the y component that is opposite over hypotenuse. That's the y component right here. And so that's opposite over hypotenuse is sine of 30. So 3 sine of 30 right here. Okay, and a similar thing is happening for our reaction force. Just be very careful though, because our angle is drawn differently. In fact, I'm going to go ahead and draw this guy over here so we can make sure that we see it correctly. So you can see that I have an x component on the top, and that x component of the force is, let's make sure I've drawn everything correctly, and this is 30 degrees, is the opposite side, that's opposite over hypotenuse. So it needs sine of 30, and you see that right here. This is the y distance, this is the x force. Going right over the top. And if we want the y force, let me make sure I did everything correctly. I did, okay. Then I need the adjacent side, which is adjacent over hypotenuse. That's cosine of 30, and that's why you see cosine of 30 right here. So it really just depends on which angle I choose. If I had chosen this angle instead, it would be different, though mathematically it would be equivalent. And then it comes out to be 3.71 kilonewtons. Remember, because it's a rolling support, we know its direction. It's just perpendicular to the surface. We just don't know its magnitude. Now with that, we can then solve either the sum of the forces in the y or x direction. And luckily for you, in the previous problem, we actually already broke this into components. We can just reuse those if we want. So the orders don't matter. Both of them have the same amount of work. So solve it in whichever order works best for you, and then you can get the answer. Now let's see how we did. With this, we see that we did choose the right direction. In most of these problems, I write the arrows in the right direction. Not always, because sometimes you forget, sometimes you make mistakes. But a lot of times you can visualize it. However, remember this. If you can't visualize it, if you can't figure it out to save your life what direction the arrow should be pointing, it doesn't matter. The only time it matters is if it gives you the number. You have to point in the right direction. If it doesn't, if it's unknown and you're solving for it, you'll just get a negative answer if you point it the wrong direction. So, as you can see, here's our final answer for the erection forces at B. We already have our erection force at A, and we're done. So I hope this helps you, and I'll see you all next time. Bye-bye.